This video will be an introduction to Unit 5 gases. On the front of the student packet, of course, is the unit assignment. And just to show us where we are heading today, we are going to, on the back of that first page, is an outline of the topics within our unit. I hope that a lot of these seem familiar. We studied some of these concepts in honors, but of course now we'll do the AP approach. This video will be the first of two that will deal with this chunk of information. So let's dig in. First, with the properties of gases. So we know that gases are so incredibly unique. They are so different from solids and liquids. What makes a gas is, of course, this relationship, that the kinetic energy is much greater than the particle attraction. If we had two water molecules, of course, water, the chin side of the oxygen will absolutely have that negative, which will be pulling for and on the positive ears of the water molecule, creating ultimately hydrogen bonding if possible. But the kinetic energy is so great it doesn't allow for it. So of course, the particle attraction is due to the makeup of the substance. And water being water, it of course is attracted to another water molecule. But the kinetic energy is so high, the particle attraction cannot show itself. And that, of course, is why the volume is not limited and there isn't a definite shape. There's a lot of empty space between gas particles. In general, there's usually, we say, about 10 diameters of separation between one water and another in the vapor state, or one vapor particle from another. In fact, the rule of thumb that if you have a substance and you have 1 milliliter of it in the liquid state, it will take on a volume of 1,000 milliliters in the gaseous state. So what a great difference due to the amount of empty space. We say the particles in a gas travel at random, chaotic motion, and we say it's a straight line until it hits the walls of a container or another particle. So if we imagine it would go and so on. Because the particles exchange places, that qualifies gases to be fluids. And we do see diffusion without us doing anything. So it happens without outside intervention. Two gases will exchange places and mix due to the motion. If you're standing next to an individual in a grocery line and they just have a lot of perfume on, well, that perfume is getting energized and is vaporizing and is most condensed at the source. But we know because of the rapid random motion, it is being diluted because it's moving outward, but also other gas particles are taking its place. So of course, if you take a couple steps away, you'll distance yourself and get more dilute because of diffusion from those cologne particles. Gases have very low density. Again, very little mass in that huge amount of space because of the emptiness. We usually use the units of gram per liter for gas density. Solids and liquids, usually gram per milliliter. Gases naturally expand to fill their entire container because of that kinetic energy. But because of the empty space, you can compress it. So if you bring the particles closer, you're just ridding of the empty space. Solids and liquids are incompressible. They don't have any of that empty space. Gases exert pressure. But how? We say gas particle, or pressure rather, is force per unit area. Forces are pushes and pulls, so how can gas particles be exerting pushes and pulls? Well, again, if this is filled with helium, a balloon, we know that the particle is going to be traveling in a straight line until it hits the wall of the container or another particle. They will collide. When you think of gas pressure, please approach it from the perspective of particle collisions. The collisions are causing pushes and pulls that result in gas pressure. The common units, and it is very frustrating that we have so many different units for gas pressure. We have the atmosphere, Pascal, kilopascal, torr, and millimeter of mercury. You never have to memorize these relationships. You will be given them, but it's good to have them in a handy location. 1 atmosphere is equivalent to 760 torr. Well, 1 torr is equivalent to 1 millimeter of mercury. So 1 atmosphere is equal to 760 millimeters of mercury. 1 atmosphere is also equal to 101.325 kilopascals, and then 101,325 pascals. Again, you don't have to memorize these, but it's good to have them written down. If you were standing at sea level, an average kind of weather day, well, we know that you are surrounded by the atmosphere. You are being bombarded by millions and millions of nitrogen and oxygen and hydrogen and noble gas molecules. If we could make a cylinder around you and extend that cylinder to the upper reaches of the atmosphere where we'd say space begins, and add up all those collisions, at sea level, that would equal 1 atmosphere. So that's hard because we've always experienced atmospheric pressure, but at least that gives you some kind of idea of the numerical value. Now, of course, that would also be 760 millimeters of mercury. Well, how do we measure atmospheric pressure? We actually use a device called a barometer. A barometer was invented by the Italian physicist Evangelista Torricelli. So that's where we get the torr. We honor him with the use of part of his last name as a unit. Imagine taking a very long test tube, about 1 meter high, and filling it completely with mercury. And then taking your thumb and causing a lid, so this was where the test tube would be open, and then overturning it into a dish of mercury, and then letting the opening go so that this would be filled with mercury. Well, here on Earth, as long as we use the length of about 1 meter, then in the open tray, some of the liquid level will lower, leaving a vacuum above it. A vacuum is the absence of matter, so there's nothing above this. Well, we measure the height of the mercury to read atmospheric pressure. Actually, a fun fact, mercury is much more attracted to itself than glass, which is what a barometer is usually made out of. So actually, mercury forms a reverse meniscus. You would measure the very top of the mercury to be your height. And we measure that in centimeters or millimeters of mercury, which we can convert to torr, atmosphere, etc. How is this measuring atmospheric pressure? We can use P subscript ATM to represent atmospheric pressure. I mean, the atmosphere is on the outside of the glass, but it also is exerting itself on the surface of the liquid of the mercury. So when atmospheric pressure increases, then more force is on the liquid and the mercury will rise in the barometer and atmospheric pressure will increase. But if pressure decreases, then the liquid can flow out and then your barometric level falls. Now, this is how we measure atmospheric pressure, and we can use readings of atmospheric pressure indirectly to help us if we're in lab and we've collected gases. All right. What factors affect gas pressure? Now, if we have what may be read in a problem as a rigid vessel or rigid container. Okay, what that means is you need to imagine this is made of steel. that means there's really no change in volume, no easy change in volume. So if we would have a rigid container filled with gas, if gas pressure is a result of the collisions of gas particles, what could we do to increase or decrease that? Well, what if we would change the amount? Now, remember, we use a lowercase n to represent moles. So we could change the moles. If we have more, there's going to be more collisions. If we have less, there's less collisions. So changing the amount impacts the number of collisions. We could also change the temperature. Temperature is directly related to kinetic energy. So if we increase temperature, we increase kinetic energy, that will impact the forcefulness and the number of collisions, both. Now, what if we didn't have a rigid container? What if we could change the volume? Well, then, of course, that would impact the number of collisions. So if we could change volume, again, if we decrease volume, they're going to collide more often. If we increase, they'll collide less often. So that impacts number of collisions. So all of these play a role in varying gas pressure. Okay, well, next we are going to move onward to talk about the kinetic theory. But I'm going to go ahead and leave that for the second video.